Today's focus is going to be working with problems that are going to require you to draw out a free body diagram. And again, a free body diagram is going to depict all of the forces that are acting on an object. So in number 17, you have a stone and it weighs, so I'm going to put in FW equals 4.9 newtons. I'm just going to sketch what this is right here. So that's my stone. Now gravity acts on the center of objects, so I'm going to put my FW of 4.9 newtons right here. It says, what is this object's mass in kilograms? Well, I also know that if I have weight and I'm on the earth, I know that I have an acceleration due to gravity of 9.8 meters per second squared. So the mass of this object is going to be found taking the weight divided by gravitational pull. So I'll substitute those in. I have 4.9 newtons. We have 9.8 meter per second squared. So this mass of this stone, it's not a very big stone. It's 0.5 kilograms in mass. It says part B, at what rate is the stone accelerated straight up if a 69 Newton force is applied in that direction? All right, so if we're going to be throwing this stone upwards, then I need to apply an upward force acting on this. And that upward force, I'm going to put FA, that's our applied force, of 69 newtons. All right, now from these two pieces of information, you have the force acting upwards, and you have the force or the weight acting downwards. And the object, it's not going to accelerate upwards with a full 69 newtons of force because it has this weight, it has gravity pulling back on it. So what we have to do is we have to look at the net force, the sum of these two forces that are acting on this. We cannot just say that 69 newtons is the only thing that's acting on this thing, because you have something else. You have that 4.9. So what we do is we subtract those because they're in opposite directions. So we subtract those two values and we should get, it should be 64.1. So I'm going to put net force equals 64.1 newtons. All right, so that's the net force. That is what is going to cause the object to accelerate upwards. All right, so I'm just trying to find the acceleration upwards. So I'm going to put A up, acceleration upwards, meters per second squared. To find your acceleration upwards, we're going to take your net force, divide it by the mass of the object, and that's going to tell us what our acceleration upwards is. So I'll have acceleration up, 64.1 newtons divided by the 0.5 kilograms that we had from before. So the acceleration upwards of this stone, once we put that into the calculator, is going to come out to be 128.8 meter per second squared. So that's one heck of a throw is what that would be. All right, we're done with that one. We're going to come over to question 18 now. Question 18 says a car located on a level highway has a mass of, so I'll put mass equals 400 kilograms. The frictional force opposing the motion of the car is, so I'm going to put F, and I'm going to put a little F down here for friction. Force of friction is 750 newtons. What will the acceleration be? Acceleration be if the car has a force that it can produce, so I'm going to put applied force of 2,000 250 newtons. All right, so if we imagine this, here's our car, and this thing has a mass, I don't have to put the MA, we have the mass of 400 kilograms. I know that the car is wanting to move forward with an applied force of 2,250 newtons, but you have this frictional force that's acting against it, and that force of friction is 750 newtons. So that's our free body diagram right here. Well, I don't have the car moving completely forward because we have friction, we don't have the car moving forward with the full force of 2,250 newtons because you have 750 of that taken away by friction. So what we have to do is we have to get the net force that's acting on this. All right, so to get your net force acting on the car, you'd have to subtract those two. And I'm going to write it out like this. I'm going to put F net, because that's the net force, divided by the mass of your car is going to get your acceleration. When you plug this in, the net force, it's the sum of the two forces. We have 2,250 newtons. The sum of those, since the 750 is acting in the opposite direction, we would subtract those. We divide it by your 400 kilograms, and you get an acceleration of 3.75 meter per second squared is what you end up with. Okay, we're going to pick up at number 19 now. It says that we have a small rocket that weighs, so that is FW, weighs 14.7 newtons. It says, what is this object's mass? Well, if we're on the Earth, we have to use 9.8 meters per second squared for the acceleration. Our mass is what we're trying to figure out. So mass equals weight divided by gravity. So the mass of this rocket, after I put my numbers in, it's going to give me a mass of 1.5 kilograms. All right, now that rocket, if we do a free body diagram of that, that means that this value right here, since that's the weight of the object, we have FW equals the 14.7 newtons. The mass of this thing is 1.5 kilograms. All right, and it says that we have the rocket is fired from a high platform, but the engine fails to burn properly. The rocket gains an upward force of only 10.2 newtons. So if we have an upward force, that means we're going to draw an arrow upwards, but that applied force upwards is only going to be a 10.2 Newton force. So there's not going to be enough thrust for this rocket to go up into the air. The weight is greater than what the upward applied force is going to be, so it's going to fall down. And this question, I'm sure it's asking, what is the acceleration downwards? All right, so acceleration, I'm going to put D downwards. So if you're trying to find the acceleration downwards, well, you're going to need to know what the net force acting on this object is and its mass. All right. So with this problem right here, what we need to figure out is not what the upward applied force is. It's not what the weight acting downwards is. We need to know what the applied force minus the weight of this object. We need the net force. So we need to know the net force acting on this thing. That's going to be the sum of the up and down forces acting on it. So with my cheat a little bit and move it over. With the acceleration, I'm going to have 10.2 newtons minus the 14.7 newtons. I am running out of space. Divided by the 1.5 kilograms. All right. Now, you do end up, when you put that into the calculator, you do end up with a negative number. And what that negative number is going to indicate is that it's going to be falling downwards at an acceleration of 3 meters per second squared. All right, that takes care of number 19. We're going to hop over to number 20. It says we have a force of 90 newtons, and that force is going to be acting straight up on a stone that weighs, all right, so we're going to have weight equals 7.35 newtons. I'm going to put a little up arrow for that force. And it has the first thing, what is the mass of this stone? All right, there's one other piece of the puzzle here that they don't give you, but you have to understand. If you're on the Earth, you do know the gravitational pull. So we're trying to figure out the mass of the stone. And then the other part of this question is, what is the acceleration of the stone? Okay. I should put the net acceleration of the stone, because we're going to try to figure out how fast that stone is actually going to be moving upwards. And we know it's going to be moving upwards because this value right there, the applied force up, is greater than the weight acting down. So I know it has to go up into the air. All right, the mass of this, we're going to take the weight divided by gravity. Okay, so plugging these in, you have mass equals 7.35 newtons divided by the gravitational pull. So that means that when we plug that into the calculator, we get a mass of 0.75 kilograms. All right, now with a little diagram here to help us out, you have the weight of this thing is going to be 7.35 newtons acting downwards, and you have an upward force of 90 newtons. The mass of it, we just figured out, 0.75 kilograms. And the upward force of 90 newtons is not, that object is not going to accelerate upwards with a force of 90 newtons because we have 7.35 newtons of force pulling back down on that object, that stone. So we need, when we're figuring out the net acceleration of this, we need to use the net force divided by the mass. So the net force is going to be the sum of those up and down forces. So I'm going to have A net acceleration equals 90 minus the 7.35 divided by your 0.75 kilogram mass, and the acceleration of this object acting, oh, hold on, there's one other part I missed. I just noticed this. It says what is the net force, and then what is the net acceleration. So we'll do the acceleration since we got it here. The acceleration of this is going to end up being 110 meters per second squared, and that is a positive value because that acceleration is going to be upwards. And then the last part, the part B that I skipped over here, part B, that's going to be the net force, and I'm going to cheat here. We're going to say part B, that's just going to be this, the net force acting on it. So you take 90 newtons minus your 7.35. So part B, the net force acting on this is 82.65 newtons. I'll put net force right here. So that's part B to this question. Okay. We get to number 21, and I have a big fear that I did not leave enough space for this. So 21, you have a weather balloon attached to a mass, okay? So you have a weather balloon here, and you got a mass that's attached to it. All right. The mass of this thing is 5 kilograms. It says, what does the instruments weigh? Well, you got gravity, and we're trying to figure out the weight of this thing. So the weight of this is going to be mass times gravity. So we'll take your 5 kilograms and we'll multiply that by our gravitational pull. And our weight of our object here is going to be, it should be 49, so 49 newtons. All right, so that's part A. So part A, you got the the weight of your the weather instruments. So we go to question B. It says the balloon is released on a calm day and exerts an upward force. Okay. So I have 49 newtons acting downwards, and then we have this upward force here, and that's going to be 98 newtons. It's going to be acting upwards on it, and that's the weather balloon that's pulling upwards on the weight of your object. So I'll put that in here. We'll have force upwards. We'll put 98 newtons. So that's part B, 98 newtons. At what rate does the balloon instruments accelerate upwards? So that is going to require us to get the net force acting on this. So part B, our acceleration upwards, we're trying to figure out what that is. So acceleration upwards, or the net acceleration, if you want to think of it that way, is going to be the net force divided by the mass of your object. So acceleration upwards, or the net force, the net acceleration is going to be the sum of all of the ups minus the downs divided by the mass of your object, 5 kilograms. So we'll put this into the calculator for part B. And part B, we get an acceleration of 9.8 meters per second squared. Now that is a positive value because the weather instruments, okay, this thing right here, the weather instruments, they are pulling upwards on that package. But notice it's not pulling upwards with a full 98, it's not accelerating upwards with that full force of 98 newtons because you have the 49 pulling back on it. Okay, so the net force here is the sum of those up and downs. All right, keep that in mind. We'll go to our next part, part C. It says after 10 seconds of acceleration, the weather instruments are released. What is the magnitude and the direction of their velocity at that instant? Now, if we go back to the kinematics, we're trying to figure out what is going to be the final velocity of this thing. All right, so if you have final velocity, VF equals VO plus A times T. If the weather instruments at first are on the ground, we know the original velocity of this is going to be 0. We know the acceleration upwards from before, that's that 9.8 meters per second squared. Now that number, just so that way you don't get that confused with gravity, that was right here. It's the same number, but it's not looking at gravity. We're looking at what that upwards acceleration is. And we'll go times our time of 10 seconds. Okay, so our final velocity after 10 seconds of this thing accelerating upwards at a rate of 9.8 meters per second squared would be 98 meters per second. And it makes sense that if for every single second you're gaining speed, or velocity of 9.8 meters per second greater for every single second. If it's going for 10 seconds, it's going to be 98 meters per second. All right, we'll go to part D here. Part D, what net force acts on the instruments after they are released? All right, now this is going to be easier if I do this. So right now, this weather balloon is pulling upwards on the instrument package. And you have a net force acting on it of 49 newtons. That's 49 newtons acting upwards. But if we break the string, okay, remember, weather balloon pulls up on the instrument package, causing it to go up. And then you have the weight of the object pulling back on it. So you have a sum or a net force of 49 newtons acting on it. 98 up, 49 down. You have a net force acting upwards of 49. If we cut the string now, you cut the string, that's no longer there, okay? What's the force that's acting now on the weather instrument package right here? What's the force? Letter D. You don't need to do any math with that because the only thing that's left after we got rid of the balloon, the only force acting on this is the weight of the object. And that's 49 newtons acting downwards. Okay, that's the sum of that acting on it. All right. And it says the last thing, letter E. Letter E here says what time lapses before the instruments begin to fall back down again. All right. So if again we go back, and I'm out of space here, if we go back to the kinematics formula, this thing right here, and plug in our values, our original velocity at the very moment that the instruments are released from the balloon, we said that they are going at 98 meters per second. All right, we have gravity pulling back on that, slowing that thing down. It's slowing it down at a rate of 9.8 meters per second for every single second. So if it's going 98 meters per second at the very moment that this balloon releases, that means that it's going to take 10 seconds for that thing to get to a speed of 0 at its apex of its height. And then it's going to start falling back down again. Okay? All right. We're going to go to number 21. Oh, that was 21. 22. This is the last one. So you have a rocket. It weighs 7,840 newtons. And it's on the Earth. So I'm just going to put this in here right now because we're probably going to have this. 9.8 meters per second squared for gravity. It says that we have a force of propulsion. So I'll put FP for propulsion for this. We have 10,440 newtons. And it says, what's the mass of the rocket? And it says, what is the upward acceleration of the object? So I'll put net acceleration here, meter per second squared. And then it says the last part, what's the velocity after 10 seconds? So I'll put velocity, question mark. We got to put in our time of 10 seconds here. All right, so a lot of information, but it's not a problem if you take it step by step. See the first part, the mass, that's going to be the weight of your object divided by gravity. So the mass equals 7,840 newtons. The weight divided by gravitational pull. Okay. And that is going to get me, need a calculator ready. We have 7,840 divided by 9.8. Get you 800. So the mass of this is 800 kilograms. All right, I'm going to sketch this out real quick. You have the weight, 7,840 newtons. We have the upward force, 10,440 newtons. And now we know the mass of this object. The mass equals 800 kilograms. Okay. We need to figure out the net acceleration. Why do I call it the net acceleration? Because we have to consider both of those forces that are acting on this. So we're not looking at just one force, you're looking at the sum of those two. So to get your net acceleration, we're going to take the net force divided by the mass that you just got. So we'll have A net equals the net force, that's that 10,440, minus the weight of the object, divided by the 800 kilograms that we got from the previous question. All right, calculator time. 0 minus divided by 800. So you have an acceleration, a net acceleration upwards of 3.25 meter per second squared. How do I know that's upwards? Well, first, that number's bigger than this one. Second, my acceleration came up to be a positive value. Okay, we go to part C. Part C, we're trying to figure out what the final velocity of this thing is after 10 seconds. So we're going to go back to our kinematics formula. VF equals VO plus A times T. You know, the original velocity of this rocket before it fires is going to be 0 meters per second. Plus the acceleration, we just figured that out, 3.25 meter per second squared. And then our time for that was 10 seconds. So our final velocity for this is going to be 32.5 meters per second. All right, that takes care of problem set number 3. If you have questions, you need to make sure that you ask right away. Do not hesitate. Typically, if you have troubles with forming the free body diagrams, you'll want to get some help right away before the test. Okay?